Okay, so today we are going to talk about parity check matrices. Parity check matrices, they are important component of error correcting codes. So error correcting codes are basically methods to detect and correct errors in data transmission or storage. So there are two things here, methods to detect and correct errors. So whenever you are doing data transmission or storage, these are important methods to like correct and detect and correct errors. Some of the common applications of error correcting codes are in Wi-Fi signals, QR codes, or satellite communications. So when you use Wi-Fi or like when you use QR codes, basically you are using error correcting codes. So when we are studying error correcting codes, this object FQ is very important. So FQ is filled with Q elements. It is also denoted as GFQ. So this Q can take values like 2, 3, 5. It can take different values. Let us take a special case of it. Let's look at this case where Q is equal to 2. So let's look at like Q is equal to 2. For Q equal to 2, the object that we look at is F2. Now we have two elements here, 0 and 1, and there are two operations that we can define. One is addition, other is multiplication. So this is how the addition looks like. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And then 1 plus 1 is 0. So this is how you define addition. Multiplication is defined as 0 dot 0 is 0. 0 dot 1 is 0. 1 dot 0 is 0. And 1 dot 1 is 1. So this is how you define addition and multiplication in GF2 or F2. Normally we will talk about this vector space, which is FQN, which is the vector space of all n tuples over the finite field FQ. So we will talk about this vector space, which is nothing but like all n tuples over the finite field FQ. So it will look like A1, A2, A3, AN. So like this is a tuple of n elements, and it belongs to FQN because each of the AI that belongs to FQ, and there are n such AIs. So it overall like this tuple belongs to FQN. So this is the object that we will look at, basically the vector space of all n tuples. So let us look at a case where Q is equal to 2 and n is equal to 3. So in this case, you have total 3 elements in every tuple. So you have A1, A2, A3, and each of the AI can take value 0 or 1. So AI belongs to 0 or 1, and there are 3 such AI. So so the possible elements which are in this case we can call it like F2 3 is basically 0, 0, 0, 0, 0, 1, and so on up to 1, 1, 1. So you notice that there are total of 8 such elements here. In general, when you are working with FQN, then size of FQN is basically Q to the power n. Like those many possibilities you have. So you can see here already that for the F2 3 case, we have Q is equal to 2, n is equal to 3, and the number of such element that we have here is 2 to the power 3, which is like 8. You can count. And whenever we talk about code, there we are interested in a subset of FQN. So we are interested in a subset of this FQN. So let's say size of C is M, then C is basically called an NM code over FQ. So N is like the vector space, like the size of the vector space, and M is basically size of code. So whenever this C is a subset of FQN, and let's say size of C is M, then C is called an NM code over FQ. So and code words are nothing but vectors in C. So you have some code word C, you have some code C, and every element of this code is basically called a code word. So let us look at this object C, which is combination of two elements like 000 and 111, and you can see that this C is a subset of basically F23, and here size of C is basically 2. So basically you have n is equal to 3 here, m is equal to 2. So it's a 3-2 code. So C is basically a 3-2 code over F2. So C is a 3-2 code over F2. So you can have different kinds of codes. So you can have like codes over F2, which are called binary codes. You can have code over F3, which are called ternary codes. You can have code over F4, which are called quaternary codes. So depending on like the field over which you are interested, you can have different kind of codes. Like F2 codes, the code over F2 are binary, F3 it's ternary, and F4 it's called quaternary codes. Okay, interesting. So let us say the C is a k-dimensional subspace of FQN. So far we were talking about C as just a subset of this set FQN, and FQN is actually a vector space. But let's say C itself is a k-dimensional subspace of FQN. Let's say C is a subspace. Then C is called, in this case, C is called an NK linear code over FQ. So in this case, you call C NK linear code. So earlier C was just taken as a subset, but let's say if C is a k-dimensional subspace, so then in that case you call your C as NK linear code over FQ. Also, you see the way we denote. Earlier we were using like this kind of notation. Like when it was a set, then we were calling it like an NM code over FQ. But now we are we are using these square brackets. So if C is a k-dimensional subspace of FQN, then C is called a NK linear code over FQ. Let's say if we are interested in NK linear code, then size of C is q to the power k. Yeah, and basically size of the vector space where it's embedded is basically q to the power n. Okay, so and basically this q to the power n we already like earlier we saw. So far we have seen that these error correcting codes are method to detect and correct errors in data transmission or storage. Just for repetition I am telling, and FQ is a field with q elements, and for the special case when we are interested q equal to 2, F2 is basically 0, 1 with 2 operation addition and multiplication defined as such, and FQN is a vector space of all n tuples over the finite field FQ. So FQN is a vector space, and basically these tuples look like this, where each of the AI they are element of FQ. For the special case when q equal to 2, n equal to 3, we looked at the example and number of total element that we had here by 2 to the power 3, which was 8. And in general, size of FQN is q to the power n. And then we looked at a subset of this FQN, and that subset, the size of, let's say that subset is M, then we call C as an NM code over FQ. And code words are nothing but the vectors from this subset. So then we looked at this special case C equal to 0, 0, 0, 1, 1, 1, and size of C is here 2. So then C will be called here a 3-2 code over F2. And then codes over F2 are binary codes, F3 are ternary codes, and F4 are quaternary codes. But let's say instead of a set, we are interested in a subspace. So let's say C is a k-dimensional subspace of FQN. Then in that case, C is called an NK linear code over FQ. So if you have a NK linear code, then size of C is q to the power k, and the ambient space where it's encoded, that has size q to the power n. Nice. So what is a message? A message is basically a short sequence of bits. So let's say k equal to 4 bits, for example. And code word is basically a longer sequence. So because you are using redundancy to encode your message into a code word, so you have a longer sequence. You are taking a short sequence and you are converting into a longer sequence. So let's say n equal to 7 bits. So this n minus k is basically number of redundant bits. So these are these extra redundant bits you are using to extend your message into a code word. So there are two most common ways to represent a linear code C. So whenever you have been given a linear code C, you can represent it in like the two most popular ways to represent it. Or one is this thing called parity check matrix, which we are discussing in this session, and there is another object called generator matrix. So that we will discuss in next session. So in the next session we will talk about what is this generator matrix. So let us look at like a linear code, which is a NK code C. So for a linear code C, which is a NK code, the parity check matrix is basically n minus k cross n matrix. So it's a matrix which has n minus k rows and then n columns. And code words are defined as those vectors which satisfy this Hx transpose equal to 0, where 0 is basically a 0 vector of length n minus k. So basically this parity check matrix, it describes the linear relations that components of a code word must satisfy. So it's some kind of a constraint, it's some linear relation that component of a code word must satisfy. So let's look at a particular example and try to understand this. So let us take q equal to 2, n equal to 7 and k equal to 4. So if we take q equal to 2, then we are interested in we are interested in the field which has this element 0, 1, and n equal to 7, k equal to 4 means that the message length is 4 and the code length is 7. So the parity check matrix is basically an n minus k cross n matrix. So n is 7, k is 4, so n minus k is 3. So basically H is a 3 cross 7 matrix. So here we have a 3 cross 7 matrix given as such. So let's say that you have this code word x equal to x1, x2, x3, x4, so on. So then Hx transpose, when you write equal to 0, gives you 3 different constraints like x2 plus x3 plus x4 plus x5 equal to 0. That comes from the first row. The second row gives you another constraint which is x1 plus x3 plus x4 plus x6 equal to 0. So that's here you get another constraint. And then the third row gives you another constraint which is x1 plus x2 plus x4 plus x7 equal to 0. So you get 3 constraints. These constraints, they give you a subspace out of this vector space. With the vector space that we are interested in is basically like f2 7, so as we said in the beginning that we are interested in this vector space fqn, and in our case here that we are looking at q is equal to 2, n is equal to 7. So f2 7 is the vector space that we are interested in, and basically our code words live in a subspace of f2 7 which satisfies these constraints. So these linear constraints, they have to satisfy, and those linear constraints are basically described by this parity check matrix. So parity check matrix describes the linear constraints that components of a code word must satisfy. So Hx transpose is equal to 0. That's what you have to satisfy. So let us take x equal to 1 0 1 1 0 0 1. Now the question is this a valid code word? I mean, this question we can ask. Now you can check here whether x2 plus x3 plus x4 plus x5, is that 0? It is 0. We have to do addition according to GF2 arithmetic that we talked earlier. But let's say if you do x1 plus x3 plus x4 plus x6, you get 1, which is not 0. And similarly x1 plus x2 plus x4 plus x7 is 1, which is not 0, which means x is not a valid code word. So Hx transpose you get a 0 1 1, and for it to be a code word we should have got 0 0 0. So since 0 1 1 is not equal to 0 1 1 is not equal to 0 0 0, we say that our x is not a valid code word. The object that you get here is called syndrome. So this is a syndrome vector. 0 1 1 is basically a syndrome vector. If this is not equal, if this is not all 0, then we say that actually some error happened during the message. So that's what we say. So error detection. Error detection is basically finding by looking at the syndrome and figuring out whether some error has occurred or not. Okay. uh, you notice that this H that we have, it had the first column of it is basically 0 1 1. So this tells you that where the errors occurred. So basically this is a first column of H, this syndrome. So for error correction, what we do is that we just flip the first bit of X, because this is where this is the syndrome vector correspond to the first column. So we had X equal to 1 0 1 1 0 0 1, and for error correction we take this one and we flip it to 0 and we get X tilde, which is what we get here. Now when you do HX tilde transpose, you find that this is all 0, which means X tilde is a valid code word. So for error correction, what you do is that first using for error detection, you find the syndrome, and based on syndrome, you figure out what operation to do, which bits to flip, so that we can correct the error. So here you see that we started with some corrupted code word, corrupted vector, and that vector give us the original code word. Okay. So here is a quick quiz that can be useful. So let's say if HX transpose is 0 0 transpose, is the code word valid? I mean, you tell me in the comment what is the answer to this one. What does the syndrome tell us? I mean, this also you can tell in the comments. And for a code with n equal to 10 and k equal to 6, what is the size of the parity check matrix? So you can look at what I discussed so far, and based on that you can tell. So I will add this the PDF on my website, and I will give a link to it. If you are interested in error correction and in general quantum error correction, do subscribe to this channel, and please spread the word around.